Welcome to Biology 1440, a lecture on an introduction to chemistry, mostly focusing on Chapter 2. Alright, so some of this may be review for you, but that's fine. Now, a few things I want to point out. All things are composed of matter. That's something that has, mass and various other physical properties. And matter is composed of atoms. And you may know the term element. That is, my own paraphrased definition would be a unit of matter that cannot be broken down into any other unit through normal chemical means. So the items you see on the periodic table of elements, these are the basic building blocks of matter. And the essential elements, these are the elements found most commonly in life. The top four, oxygen, carbon, hydrogen, and nitrogen, make up 96% of the tissues in living things. Now, a few of these other elements, somewhat, I guess you could call them essential as well, but they're not the big four. So if I test you on some, it'll likely be the big four. But calcium, phosphorus, potassium, sulfur, those are also important, but they're only around 4%. Now, those that make up even less of the percentage of the elements found in life are the trace elements. And these are important for health and things, but you just don't find them in very high quantities. So things like iron, which you'd find in hemoglobin, or iodine, and other elements that are just not needed in very large quantities. So elements are this basic idea of this building block of life. And then this term molecule, which I'm sure you're familiar with. Think of that as, remember, elements are these building blocks of matter. They themselves are composed of atoms, right? So you can have an element of gold, or an atom of gold, or an atom of hydrogen, or an atom of carbon. So when you take more than one atom and stick them together, that's called a molecule. For example, O2 is known as molecular oxygen. That's two oxygens stuck together. Now, a type of molecule that's really common is called a compound. A compound is when you have a molecule that consists of more than one element. So CO2 has carbon and oxygen. That is a compound. So it's a type of molecule that has more than one element in it. Up here we can see sodium, that's an element. Chlorine, that's an element. You combine them together into a compound, sodium chloride. So just some basic terminology there. I'm sure you're familiar with the periodic table. There's a version of it in your book. We'll talk a little bit about what some of the most important numbers mean, but you can see that here and refer to it as needed. Now, atoms, which are the building blocks of elements, consist of several subatomic particles. You can see them labeled here. This area in the middle is known as the nucleus, and the nucleus can consist of protons, which are positively charged, neutrons, which are negatively charged, and electrons out here, which are not part of the nucleus, but outside the nucleus, have a negative charge. And typically, the number of electrons equal the number of protons, and that's in a neutrally charged atom, so an atom that does not have an electrical charge. And different atoms, so these are the atoms of different elements. One thing that makes them different from one another, one of the major things, is the number of protons. So hydrogen has one proton. That's what this number means here. So let's look at this symbology here. Atomic number, which is right here shown like this number 8 in oxygen. That's the number of protons in the nucleus. Excuse me. And that's how you define what the element is. And then you might also see, we don't see it on this one, but you might also have the atomic mass, and that is when you add up the atomic number and the average number of neutrons in that element. You get the atomic mass, and that atomic mass is often a decimal, but that's fine. So we could figure this out. So for helium, we could see the atomic number is 2, the atomic mass is 4, so that would mean there's 2 neutrons in your average helium, okay? Because 2 plus this number 2 equals 4, okay? Let's look at hydrogen. We don't see the atomic mass for hydrogen up here, but hydrogen is one of the weird ones. It has a proton, but it does not have a neutron. So it's just a proton and an electron, and you can see that electron drawn out here. Now, you might also know this. We have these energy levels of these electrons drawn here. The inner energy level can hold up to 2 electrons, okay? And then it's full. Now, we can see that here with helium. There's 2 there. It's full. It's happy. Okay? It's content. All of the other energy levels, so if you have more than two electrons, you're going to have more energy levels. The outer energy levels can hold 8 electrons. This is called the Octet Rule. They are satisfied, they are happy when they are completely full. So here we have argon with number of protons are 18. So in the first energy level, we have 2 electrons, right? And then in the next energy level we have 8, and then in the next one we have 8. So all the way out to this outer level, which is also 8. And argon has a full octet, a full valence electron shell. If you don't know that word, look that up. Valence electron shell. That's the outer energy level, the valence shell. And in this case, it's full, and therefore argon is unreactive, right? Meanwhile, chlorine, if you look over here, it's not full. Look out here. It's missing an electron. That means chlorine is going to be very reactive because it's almost full. It really wants another electron to be stable, so it's going to borrow or steal electrons quite readily. Now, if all of this is new to you, you can rewatch my explanation here, but please be sure to read the chapter thoroughly and watch any videos that come along with Mastering Biology. Remember, you can also quiz yourself on Mastering Biology to help this stuff sink in. So I think we've already talked about this, but the atomic number is the number of protons. The letters here are the elemental symbol, and the atomic mass is the atomic number plus the average number of neutrons found in that element. The number of neutrons can technically vary, so that's why you end up with these decimal places. So there's hydrogen. There's a proton in the middle and an electron orbiting, and that's the most common element known in the universe. It's found all over the place. A very simple atom, but very common. Now, helium, on the other hand, has 2 electrons, 2 protons, and 2 neutrons. So one thing I want to point out is that hydrogen shows up right after the Big Bang. It's kind of a product of the Big Bang. But not really, as far as we know, the other elements weren't really formed yet. Maybe some heliums were formed then. I'm not an expert on the Big Bang, but what we do know is that in stars, which are where nuclear fusion takes place, hydrogen, I'm not going to explain this entire diagram, but hydrogen can come together and then come together again, and eventually through this process of fusion, which is somewhat complex. So once again, I'm not going to make you draw this or anything, but I would like you to know that these elements are formed in stars through the process of nuclear fusion. So 2 hydrogens come together here, and 2 more over here, right? And eventually their products join together again. So you ultimately end up with a helium atom. So you can fuse 4 hydrogens together. Some of parts of those nuclei become neutrons, for example, and we fuse the protons together, and we end up at the end with a helium. So that's accomplished in stars. And if we look at a star, if the star is massive enough, it'll have these different layers where there's more and more heat and pressure and things going on. So out here we have hydrogen, right? Inside of here we have helium forming. If the star is big enough, we'll form carbon deeper inside, oxygen, all the way down to iron in the middle. Okay, and then if this star eventually dies and goes into a supernova and explodes, it throws those elements out into space, and that is the origin of all the material we're made of, are these supernoval explosions from way back in the past in the universe. That's what they mean when they say we are all made of star stuff. We are literally made of elements made in the hearts of stars. So we smush various numbers of hydrogens together to get helium. We can squish different heliums together to get carbon, and so on and so forth. Now, isotopes are atoms of an element, so they have the same number of protons, but they might have different numbers of neutrons. Okay, so carbon-12. So when we say carbon-12, let me go back for just a second here. We're talking about carbon-12. Let's see, where's that periodic table at? Do we have carbon on here? Yeah, so here's carbon. You can see it says 6 right there, right? Well, what we're talking about when we say carbon-12 is not the atomic number, but the atomic mass, okay? The number of protons plus the number of neutrons. And most of your carbon is carbon-12. 6 protons, 6 neutrons. But there's also carbon-14. And so some carbon has 14 neutrons. It's less stable. Actually, a lot of isotopes are radioactive, meaning they're unstable and they release subatomic particles. Carbon-14 will actually decay over time into nitrogen. So isotopes, once again, are atoms of an element with varying numbers of neutrons. So different numbers of neutrons than you might expect based on the periodic table. That's why I said the atomic masses are averages. So if we go way back in this slideshow to the first, so let me stop here real quick. So there's that atomic mass number, right? If we go all the way back to the beginning here and we look up, let's say carbon, it'll say carbon and it'll say its atomic mass is 12.011. Why is it not just 12? Well, it's averaging in the abundance of carbon-12 versus carbon-14, and so that's what that number comes from, okay? Because of those isotopes that exist. Now, carbon-14 is not very common, so carbon-12 is more common, so the atomic mass is 12.011. Now, if we go out to those electrons, we talked a bit about the nucleus. So the number of protons is the same in various elements, or within an element, I should say. Like all carbon has the same number of protons, but it may have different numbers of neutrons. Now, if we go out and look at those electrons, typically the number of electrons equals the numbers of protons. So electrons have a negative charge, protons have a positive charge. Those electrons can be found in different energy levels or energy shells. This is not like an orbital of a planet. This is just like a general area where electrons might be found. But if electrons have a little bit of energy, they're found closer to the nucleus. Electrons that are found way out here have, in an outer energy shell, have more energy. Okay, and they can change. If an electron loses energy, it will fall closer to the nucleus and be found closer to that nucleus. If an electron gains energy, it will be found further away from the nucleus. Okay, so picture like an electron on a set of stairs. If you're at the top of the stairs, you have more energy. If you lose energy, you get closer and closer to that nucleus. Okay, this is going to become very important later when we understand how respiration and photosynthesis works. We can charge up those electrons and give them lots of energy, and then transfer that energy from one reaction to another. Now, if we actually look at the actual orbital shapes of electrons, it gets more complicated. So within that first energy shell, you're going to have just this spherical looking orbital. Okay, this is the area where the electrons are likely to be found, right? In the second shell, the next energy level, you're going to have a spherical orbital, but you're also going to have three of these kind of balloon-shaped orbitals as well, these 3 2p orbitals that each contain 2 electrons each. Okay, so you're going to have one of these with 2 electrons in it, and each of these orbitals can have 2 electrons each. I'm not going to go down this rabbit hole and make you, learn this exactly, but if you're taking chemistry, you may see some things like this soon. I would like you to know how many electrons those various energy levels hold, though, because that's going to be very important to determine how various atoms will interact with each other. So getting to that, here we have hydrogen atoms. 2 of them, right? And they have 1 electron each in their outer energy level, and they can hold up to 2. Now, they would prefer, in quotes, they don't think or feel, but they would prefer, right, to have 2 electrons. And they can accomplish that by getting together and sharing electrons with each other, forming a chemical bond. So in this case, their outer energy level, this one has 1 electron, this one has 1. That's what this kind of gold cloud represents, is the position of those electrons. They can share an electron each, therefore completing that outer energy level. This is called, covalent. This is a covalent bond, because that outer energy level, the very outer one, is called the valence shell, or the valence level. And if they're sharing electrons in that outer level, it's called a covalent bond. Now, one thing I want to point out is that different atoms have different electronegativities. And electronegativity is how much attractive force an element has for electrons. Okay? So the more electronegative you are, the more you can grab on to electrons. So for example, in this drawing we have HCl. And we have, so this is hydrogen and chloride, right? And so this Cl is more electronegative than this hydrogen. So it borrows, even when it's sharing electrons with hydrogen, it borrows that shared electron more than it shares electrons with hydrogen. And so because those negative electrons are hanging out with this chloride or chlorine atom over here, a lot. That means that this symbol here stands for a slight negative charge. Okay, this is partially negative. It's a partial charge. It's a very weak charge, but it's because the borrowed electrons in this relationship are hanging out with this chlorine more than they're hanging out with this hydrogen. I called it a chloride at first. That's not technically correct. If we break this bond and that chlorine's hanging out by itself and it's stolen an electron, it would be a chloride. But right now it's just sharing electrons with hydrogen, and it's borrowing electrons more than it's sharing, which makes it a little bit negative. So this little symbol here means that it's slightly negative, which means that this hydrogen is slightly positive in this relationship. Okay, you can see on this color chart they have the electronegativity. So things that are in red are very electronegative. Things that are orange are a little more electronegative, but are a little bit electronegative, and things that are kind of purple are very weakly electronegative. So notice chlorine being very electronegative, hence it borrows electrons more than it shares. Another very electronegative element that's going to be very important in Bio 1, oxygen. Oxygen is very electronegative, and we'll talk about the consequences of that. There are numerous consequences of that, which we'll talk about. So, covalent bonds. There are 2 types. So this is when two elements are joined together, or how should I put this? The atoms of elements are joining together, right? And they're sharing electrons to fill that outer energy level, which can hold up to 8. And there's 2 ways to do this. We can have nonpolar covalent bonds, and we can have polar covalent bonds. So on the left side of this screen, we see nonpolar covalent bonds. This is when you have atoms, either the same atom sticking to itself, right, like 2 oxygens stuck together, forming molecular oxygen, or if you have two atoms that have very similar electronegativity, like hydrogen and carbon. They share electrons about equally. And so when they stick together, there's no charge. They share equally, so there's no electrical gradient there or anything, and they are said to be nonpolar covalent bonds. Now, polar covalent bonds arise when you have one atom sticking to another, and one of them is very electronegative and the other one is not, like we saw in the last slide with hydrogen and chlorine sticking together. What happens then? Electrons are borrowed more frequently by the more electronegative atom, making it a little bit negative, and the less electronegative atom becomes a little bit positive. Okay? What's interesting is when you form these new bonds, like say you're making CO2 that we see in this case, those electrons get pulled close to that oxygen because it's very electronegative, and since they're being pulled close to its nucleus, they might actually lose a little bit of energy. Now, these polar bonds will result in some interesting characteristics in the molecules that we'll see. An emergent property, if you will, of the molecules. We talk a bit about emergent properties in biology. That's the idea that you have these different smaller components that have their own properties, and then when you stick them together, new properties emerge at the next level of that organizational hierarchy, that biological hierarchy that we talked about in the first lecture. These new traits arise. For example, hydrogen and oxygen have different electronegativities, and when they stick together, the oxygen becomes a little bit negative and the hydrogen becomes a little bit positive. Okay, that makes a polar covalent bond. That makes water molecules polar. They have a positive side and a negative side. That in turn has the emergent properties arise of water's ability to cool off the climate near an ocean, water's ability to cool you off when you sweat. These are these amazing properties that emerge due to the differences in electronegativity between water. I should say between oxygen and hydrogen. So we can see here lots of different covalent bonds. These sharing of electrons. Here's hydrogen, molecular hydrogen. So two hydrogens, each one sharing an electron. You can draw these like this. You can label them out this way, where we have one hydrogen here, one here, and then there are two electrons shown between them. Or a bond like this can be shown with a single line like this. So this is when each one is sharing an electron. Here's molecular oxygen, O2, and in this case we have a double covalent bond. Each oxygen is donating 2 electrons to that bond. So that can be drawn this way with 2 dots from each oxygen, or what almost looks like an equal sign indicating a double covalent bond. Here's water that I just mentioned, hydrogen and oxygen stuck together in a covalent bond, and methane. So you can just see, here's what it would look like, kind of, you could imagine it as a cartoon, these electrons being shared. Here's how we might write it in our notebook, or see it in a textbook when a drawing is not necessary. Now, that was covalent bonds. That's what holds matter together very strongly. That's what holds you together for the most part. There's another kind of chemical bond called an ionic bond. This also has to do with electronegativity. This is when the difference is very large. I should say difference, not different. The electronegativity difference is large. And so instead of borrowing an electron, one of the atoms actually steals the electron. So this generally occurs when the electronegativity difference between the two atoms is around 2. Electronegativity has a value, right? And when that value is close to 2 in terms of how different they are, then rather than borrow electrons, the electronegative one tends to steal electrons. So here we have sodium, which has in its valence shell a single electron, and we have chlorine, which has 7 electrons in its outer shell. So what happens is it just steals that electron from sodium. Now, what would that cause to happen? Now suddenly sodium has 1 fewer electrons than it does protons. That means sodium now is positive. Chlorine now has one extra electron, one more electron than it has protons. It now is negative. So now we have formed ions, and we call this Na plus, or a sodium ion, known as a cation, because cations are just another way to say a positive ion. Chlorine becomes chloride in this case. That's a chlorine ion, right? So chloride, Cl minus, known as an anion, which is a negative ion. Now what's funny though, now that this is positive and this is negative, now these two are actually attracted to each other due to their different charges, and they stick together forming table salt or sodium chloride. So they didn't covalently bond together. One stole an electron from another, which changed their charges, and now those opposite charges are attracted to one another, just like opposite sides of a magnet are attracted to one another. Hydrogen bonds are the last kind of bond I want to mention. I alluded to it earlier when I talked about the unequal sharing of electrons in water. So what happens is oxygen borrows electrons more than it shares with hydrogen. That makes oxygen a little bit negative, makes hydrogen a little bit positive, and because of that, kind of like in an ionic bond, it's attracted to other atoms that have a slightly negative charge. And that weak bond, this is a very weak bond, weaker even than an ionic bond, is known as a hydrogen bond. And we'll talk more about those when we talk about water itself in chapter 3. But hydrogen bonds are the bonds that allow water tension to form. They are bonds between different water molecules, and they occur because of the weak charges, the weak differences in charge between parts of the molecules that we see here. So a few things I want to point out. We're gluing together these atoms. They're sharing electrons, or they're stealing electrons, or they're attracted to one another in some way. One thing that's really important to note, especially if you're going to be doing anything related to medicine, is that the structure of a molecule is intimately tied into its function in a living thing. Structure is, think of structure like a key. If you don't have the right shape of your key, you can't unlock the door, right? And so you'll see all these drawings showing you the basic structures of some of these things. Those are sometimes important to understand. For example, we have a natural endorphin shown here, this complex. All these little circles represent atoms in this molecule, right? This is its structure, and it docks with your brain cells and causes a natural kind of a good feeling, okay? We can make chemicals or find chemicals in nature that have a very similar shape to this. So here is morphine, very similar shape. It will also fit in that same receptor in your brain cells. It will dock to those, causing an effect in the body. This would be impossible if it didn't have a similar shape. So structure and function are very important to understand if you're going to be understanding how life works. When we're making these different chemicals, remember we're causing chemical reactions to happen. Your cells are facilitating millions of chemical reactions as we speak. And so we should just define what that means real quick. So a chemical reaction is when you take reactants, so in this case hydrogen and oxygen, and then there's a reaction which allows them, a chemical reaction breaks and reforms chemical bonds. So a lot of times we're making new covalent bonds. So in this case we take hydrogen and oxygen, and we break the existing bonds, and we make brand new bonds, and we make products. So the final product here is water. So hydrogen plus oxygen yields water. Okay, and what's really cool is when you do this reaction, it also yields fire. We'll talk more about that later. But we have produced water from this reaction. So water is the product. The reactants were hydrogen and oxygen. This is going to come up again later when we look at biological processes, these metabolic processes in the body, where you can have carbon dioxide and water. CO2 in water. A little bit different here than the one we saw in the last slide, right? This is CO2 in water. They can be joined together using sunlight energy to produce glucose and oxygen. So another example of a chemical reaction. Glucose then is something that we might eat and use for fuel. So understanding the basic parts of an atom and the kinds of chemical bonds that can occur are very important for understanding the rest of Bio 2, or I'm sorry, Bio 1 and Bio 2. But for Bio 1, please be sure you know what the parts of an atom are, understand where you find the most energy-rich electrons, on the inner or the outer electron energy level. Which one is it? Know about the Octet Rule. So the outer energy shell is usually full when there's 8 electrons present. And so you'll need to understand several things to do well on questions over this chapter. That includes electronegativity, and polar and nonpolar bonds. So a question on a test might be, why are there polar and nonpolar covalent bonds? And then you'd have to describe, it's because of the difference in electronegativity between the two atoms involved in this chemical bond. You want to be able to talk about ionic bonds and hydrogen bonds, and what a product is, what a reactant is in a chemical reaction, things like that. So be sure to practice some questions on mastering at the end of the textbook and other places, and I think you'll do just fine if you put a little bit of study time in. I'll see you in class.